Right, welcome back. Today we're going to talk about crystal lattice structure, which is going to be the arrangement of ions in an ionic sample. So if you didn't catch it from right here, this means we're going to be talking about ionic compounds instead of about covalent compounds. So this is going to be talking about the strength of the sample, the forces in between individual ions that holds the whole macroscopic scale together. And we have to first identify if we're talking about a ionic substance or a covalent substance. So here we're looking for a non-metal to, a metal to a non-metal, as compared to on a intermolecular force, we're looking for non-metals to be involved. And we need to also understand this concept of something called a formula unit. In an ionic compound, when we talk about a formula unit, we're talking about one sodium and one chlorine in the case of this picture over here. So a sodium and a chlorine is a formula unit. That's what we would call the formula of that substance. But in an actual large-scale crystal, we're talking about billions of these put together. And that interaction between all of the different ions, that's going to be called the crystal lattice structure, and that's also going to be what's going to determine the lattice energy. So crystal lattice structure is going to be that arrangement of these cations and anions, and it's arranged in such a way that it minimizes repulsive forces and maximizes attractive forces. The lattice energy of that substance then is determined by looking at a melting point or a boiling point of that substance, and that's going to be the energy stored in that lattice. In other words, how much energy does it take to break that force in between the positive and negative ions? The larger the energy, the stronger that lattice structure happens to be. So there's two factors when we consider what makes lattice energy high or what makes lattice energy low. The first and the more important of those two factors is the positive or minus charge. So if you're a plus or minus 1, that would be considered like a weak factor for determining lattice energy, whereas if you're a plus 3 ion or a minus 3 ion, that would be a strong factor. So if you have a plus 3 with a minus 3, that's going to be the strongest combination of ions that you can put together. That's going to create a very high lattice energy. So that means group 3 connected to group 5, for example, in the periodic table, if it was an ionic substance, it's going to have a high lattice energy. On the other hand, a group 1 connected to a group 7 is going to be relatively low. If you happen to put like a plus 1 with a minus 3, then you have to start comparing, if I'm comparing multiple ionic substances, am I looking at a plus 2 and a minus 2? That's harder to tell what's going to be stronger. So plus 1, minus 1 are weak, plus 3, minus 3 are going to be strong. Pretend that these are like magnets. The second factor, and it's less important than this, all things being equal, less important, is the size of those particles. Now, big particles can't pack as tightly as small particles can. Think of packing like volleyballs compared to packing marbles. If you pack marbles together, the amount of extra space around those marbles is a lot smaller than volleyballs. There's going to be a huge amount of space in between those balls. And what that's going to do is that's going to minimize the force of those charges that we've already established. So the farther apart you are, the less you can be attracted to your neighbor, because there's less, there's more distance between those charges. So what does that look like? If we're going to be asked this on a quiz or on a worksheet, you're going to have to know how to solve this. So the first thing that you need to do is you need to identify, am I looking at an ionic compound? So of these 4 down below, which one's going to be ionic, which one's going to be covalent? Choice E isn't going to be a factor here because it's 2 nonmetals stuck to each other, so we can cross off choice E. Then when it comes down to the rest of these, you have to look at each ion. If I was doing this problem, I would split these in half, and then I would decide what's going on as far as charges here. So here is a plus 1, this is a minus 1, this is a plus 1, this is a minus 1, this is a plus 1, this is a minus 2, this is a plus 1, this is a minus 3. So we can see that the first part of our particle shouldn't be having a huge influence on the overall melting point or boiling point because they're all plus 1s. So that means the second portion is going to be the more important portion of these compounds. So since this is a 1, this is a 2, this is a 3, 3 is the highest. This is like a weak magnet with a strong magnet. This is going to be the highest lattice energy. So the correct answer to this one would be D. It would have the highest melting point or boiling point based on this trend, which would mean it also has the highest lattice energy. So after watching this video, you should understand what the word lattice energy means. It's the energy that's holding ionic substances together, and then the structure is going to be the arrangement of those particles to minimize repulsive and maximize attractive forces. And then you should be able to understand how to determine, given a list, which substance has the highest lattice energy. First, recalling that charge is the most important, plus 3 minus 3 are going to be the strongest, and then size of particle is the second factor. Hope that helps.